So that's when you push the button. We'll have a chance to talk more about review stuff, but just wanted to bring that up about the timing of that. And so the other important thing for me to mention before we get started is next week, I'm not going to be here in person. So it's virtual meetings. So you can log in through Zoom the normal way. You can come here and log in the room to Zoom. The room is still booked if you want like the camaraderie of sitting here together, which is fine. And it'll still get recorded into Panopto the way it normally does. If something goes wrong, because I'm going to be at meetings next week and I can't log in, I have put a link to a previous year's version of those lectures that you can go hear. So if you're like, where is he? What's going on? Why is this not happening? Just watch the YouTube version of the old one. One of which is like bizarre and during the pandemic, like me sitting at home, like whatever. And then another one, which is from before that. So pre-pandemic, which is just me standing in a different classroom that's actually upstairs that no longer exists. And it's like my laptop pointed at the screen. So very old fashioned. But anyway, those are backup plans if something else fails. And when I'm away, I'm going to be away a few more times in the semester and we'll do that same system. So in theory, it's just going to switch to Zoom. But if it fails, I'll have a pre-recorded one to share instead. That makes sense? Okay. All right. So what did we talk about last time? Anybody remember? It's been like a week. Everybody thought it was good, well rested now. Anybody remember? Rotating reference frames. Rotating reference frames. So we started talking about the Coriolis force and the centrifugal force. And stop talking about the centrifugal force because it doesn't really matter. You just lump it in with gravity and forget about it. But then Coriolis force is going to be important in almost every major balance we talk about. And so then we talked about the Taylor-Proudman theorem where the Coriolis force is totally dominant. It's like the only thing important. And that says that it stiffens the fluid in the direction of the rotation axis. So there's no overturning or shear in that axis. And then we talked about inertial oscillations, which is just these wobbles that happen on a rotating planet. Like, because like you can, if you're going around in a circle, the Coriolis force is just pushing you inward. So you just keep going around in that circle over and over again. Remember that refreshing things? Okay, so today we're going to talk about a steady state balance between the Coriolis force and something else. And this is the first of our steady state balances between the Coriolis force and something else. And this, well, depending on who you ask, this is either the most important one or the second most important one, but it's top three in oceanography. This is a really big deal. So this is the Ekman momentum balance. And upwelling is the major consequence of the Ekman transport, which is one of the things we're going to talk about. And so we're going to keep talking about this next Tuesday. And we're going to kind of talk about it, and we're going to talk about geostrophy, which is the other of the top three. And then we're going to put them together and talk about how the gyres work, which is a combination of the Ekman part and the geostrophic part, plus some magical stuff about pressure fields and vorticity and other things that are going to be complicated to explain. But that's going to give us the sense of why the gyres work the way they do. And that's going to be sort of the central, deep, dynamical explanation of this class. So the next two papers are on topics involved in those pieces. And then the last paper will be on a like kind of hodgepodge of topics. You're free to choose again, kind of like you did this time, except next time you'll have a lot more tools to use than this time, which was kind of like just write a paper without any information, which is kind of an exciting thing to try. So anyway, does that make sense to everybody? Okay. What's wrong? Is that right? No, that's wrong. That should not be there. It's not next Thursday. It's actually next Tuesday. Sorry, I forgot to delete that. That was from today, not from last time. Okay. But so next time we're going to have an Ekman convergences in the gyres pressure. So that's the next piece. So the next thing to come up is also incorrect. Well, no, it is the review. The review is to do today. So everybody has figured out how to do a review. Everybody's figured out like where you cut and paste it into Canvas. Or upload it in Canvas or something like that. So I haven't looked at your reviews yet, except for skimming them in brief detail, but I'll upload mine. Take a look at yours, and then all those will get graded kind of as we go. So you'll have feedback on the reviews before you have to do another review. But that seems like low pressure to me because it's more about getting reviews on the paper back first. That makes sense? Okay. All right. So we get to do our review of balances, our daily activity. So the hydrostatic balance, who wants to explain what the hydrostatic balance is? What does hydrostatic mean? That word? It is the balance on the vertical. Word hydrostatic means the water is static. It's not moving, and so it's a balance. It's just the pressure that's there in motionless water. But it turns out to also be the dominant pressure in the vertical for things that are just kind of sitting still, like ocean water that's not moving very fast. So it's a pressure gradient force. It's the vertical component of the pressure gradient force balancing the gravity. And so this is the thing that gives us the 1 decibar pressure increase per meter in the ocean. Okay. Taylor-Proudman theory. I already said what that is. It's not obvious at all that you need all 3 of these terms because we derived it in a different way. But it turns out that all 3 of those terms are involved in the Taylor-Proudman. They're all allowed to be non-zero. The other ones need to be 0. So they need to have small friction, small Rossby number, and so on. Inertial oscillations are just the Coriolis and time derivative and nothing else. All the rest goes away. Okay. So you're starting to, I hope, to get the sense that like a dominant balance, what it is it's kind of pull a handful of terms out of the equation and just solve that reduced equation. And consistently, we're throwing away the nonlinear term because that one is hard. So we're just going to be pulling different choices of the linear terms or in conditions where they could be made linear and then balancing them because we can actually solve those equations and think about what they look like. In the end, we're going to put them all back together and think about combinations of multiple balances kind of working together. And we're going to see that a little bit today. In the Ekman layer, because the Ekman layer is kind of a deviation from something else. All right, so we're going to have an opportunity to talk about review questions a little bit later, but we're going to introduce the Ekman balance between Coriolis and friction or turbulence. See what the difference. The Taylor-Proudman theorem is violated because the introduction of friction. So what does that mean in terms of Taylor-Proudman means it's stiffened. So if it's not stiff, then what is it doing? It's shearing. So it will be moving at different speeds and actually different directions as we go through the Ekman layer. And it's because there's friction there to break the Taylor-Proudman theorem, but everything else is the same conditions as the Taylor-Proudman theorem. Ekman layers are important for coastal and equatorial upland, so we're going to talk about that a little bit. And that will sort of motivate you maybe for your next paper choice of topic. You can start thinking about it. People, one of the things that people might do is choose an upwelling region and think about how it works. Like what's the variation in wind, and then what's the variation in stratification, upwelling, offshore flow, those kind of things. Like should be able to connect them all together through the Ekman balance once we have that thesis out. Okay, so here's a hint. Here's the Ekman layer balance. It's this term, which is the viscous term. This is also a turbulence parameterization, a very crude one. So I'll talk about in a second as what I mean by that. Balancing this Coriolis term. Okay. All right. So this was our Taylor-Proudman theorem. Here's the stiffening. You don't, in the direction of F, So in the vertical direction or along rotation axis direction, you don't have any change in the velocity vector. It's the same all the way down. So remember, it flows in those sort of sheets or curtains kind of flow that we saw in the tank. No shear in that direction. But if we add another term, we don't throw that term away and we keep it in there, we're going to break that. And so let's get a little bit of grasp on what the situation that we're thinking about is. So the Ekman layer, there's an Ekman layer at the bottom of the ocean, which we're not going to talk about very much. The main one that people are thinking about is the Ekman layer at the surface of the ocean. And what's happening is that there's wind stress, which is causing turbulence, or at least causing stress. So there is momentum going from the atmosphere into the ocean and pushing the water. And there is a finite depth layer where that wind stress is felt directly. And there's a little bit of shear in that layer because of that. So down here in the interior, you might say, oh, there's a Taylor-Proudman flow going on down there. I don't know what it is, but it's fairly constant in the vertical. But then when I get into the Ekman layer, there's a shear. So what we want to do is we want to think about how big the shear is, how it depends on the wind stress, how it depends on the Coriolis parameter, how it depends on depth, how its direction's fixed. That's the question. Okay, so this is the kind of side view, and there's nothing too specific here except there's a U and V, so it could be in two directions. We don't even know, and this is the part that's weird about the Coriolis force, that flow is going to be in the direction of the wind. In fact, it's not in the direction of the wind. Okay?
Does the Taylor-Proudman theorem apply to the whole depth of the ocean?
It does under those conditions where there's constant density, or there's a slight generalization that makes it, you can have the density vary, but in a boring way. And then no friction, small Rossby number. So the big one that changes in the middle of the ocean is that constant density approximation. We're going to find out that when the density varies kind of horizontally, we're going to see that Taylor-Proudman is violated by that one. But the first violation of Taylor-Proudman is this frictional piece up here at the surface. Okay, so we can think about this in a really simple force balance. So our force balance is Coriolis is going to balance the force of the wind. So there's momentum being put in continually from the wind. The Coriolis is going to balance it. Okay, so Coriolis arrow, wind arrow. The flow, in order to have the Coriolis oriented that way, has to be going this way. Because the Coriolis force is F cross V. So V has to be perpendicular to the Coriolis force and also to F. So how do we get that? F is coming out of the page, like we're looking from above. So F cross V, we got to have something like that. So it should be going, I don't know, maybe it's looking this way, F cross V, that way. Why is that upside down? Oh, it's because I've written it here as a force. Sorry. It's whether it's on that side of the equation or this side. If I write it here as a force rather than an acceleration, it's minus F cross V, which is F cross V minus. So the balance of forces is the Coriolis force, so minus F cross V. Balance is the wind. That's all on this side of the equation. That's what we want, which means that the velocity, in order to get a Coriolis force like that, has to go this way. Okay, so a different way to put it is the velocity in the northern hemisphere is 90 degrees to the right of the wind. So you push on it and it goes that way, which is really weird. It's also not an acceleration in that you push on it with a constant force and it moves at a constant rate. It does not accelerate. And we'll get to that in a little bit, but this is a weird set of ideas. Okay, let's go back to this friction versus turbulence thing. So if we imagine having two kind of classes of water, maybe one that's moving slow and one that's moving fast, which in the frictional case, that's maybe the right way to think of it. The higher velocity water is closer to the wind, so it's moving that way on the top, and it's moving less here. The molecules are bouncing around because of heat. And so the molecules are kind of jumping back and forth. Every time a molecule jumps down here and has the light blue, it has less momentum, or it has more momentum than its environment. And every time a dark blue one goes up there, it has more momentum than its environment. So instead of a sharp momentum that's like big up here, drop down, small down here, this starts to smear that out because you're spreading out the high momentum into the low momentum water and the low momentum into a high momentum water. So over time, you'd expect it to go from a sharp jump to a less sharp jump over time. Okay? So that viscous term at the end of the equation, the new nabla squared V does exactly that. The viscosity is telling you about how fast those molecules are doing this smearing out. And that gradient is getting smeared out by the nabla squared. Okay? Everybody kind of get gist of that? What if it's turbulence, like big hunks of water instead of molecules? We could just wave our hands and say they're the same. Sometimes you'll get a fast eddy going up into the slow part, down into the slow part, or a slow eddy going up into the fast part. And then we just smear out that sharp jump in momentum and make it wider. So why is that not a good approximation? What's different about an eddy versus a molecule? Eddies are bigger, yes. Eddies are also like part of the fluid in that they're like bumping into and affecting their neighbors. The molecules, you can kind of imagine them as like shooting through empty space until they crash into something. So that bumping around, talking to your neighbors means that actually in a turbulent flow, the talking to your neighbors term is that nonlinear term. So in a turbulent flow, the biggest term is often that nonlinear term. And pretending that that nonlinear term, you just kind of forget about the details, smears out to be something that looks like the viscosity, is a big oversimplification of how interesting turbulence is. So kind of first order, what does turbulence do? It smears out the sharp jumps in velocity. That's probably right, and it has the right direction. Since the eddies are bigger and maybe moving faster than the molecules, you might expect the viscosity out front to be bigger. That's also true, but the viscosity won't explain all the things that happen over here, because this is a more interesting flow than the molecules are. Okay, so we're not talking a whole lot about turbulence in this class, but I wanted to motivate why we preserve this term in the external force term. So we have this viscous term, and we put a little E on it that's Ekman maybe, or maybe eddy, depending on what you want, but it's going to be bigger than the molecular viscosity. The molecular viscosity in water is like 10 to the minus 6 meters squared per second. And the one we're going to put in here is more like 1. So like 1,000,000 times bigger for the turbulence. It would be kind of typical. Okay. All right. So what have we done? We take our big equation. We're going to put in for a viscous or turbulent term there. We've got the Coriolis term now. So we're on a rotating planet. We want to think about this little shear part, not the total velocity, because we're not going to explain that part again. We already have a Taylor-Proudman theorem or something else, which we're going to talk about when we get to geometry to explain that. We just want this little difference. So if I call the difference VE, Coriolis force acts on the difference plus the other part. The other part is doing whatever magic it's doing. Coriolis is matching with all of the other things. But the other part doesn't affect the friction because the friction is only occurring in this Ekman layer. And the only thing that the friction does is it causes that shear. So we can make a balance which just says the friction on the, sorry, this could be VE here, is equal to the Coriolis on VE. And we're not worried about any of the other terms in the balance. We're just going to see if we can balance those two. Okay. And this is that velocity of the eddy. So the viscosity goes like the velocity of the eddy, the length scale of the eddy. So the eddies are bigger. So both of these are bigger. So the viscosity is bigger. So we could take the ratio of these two terms, like we've been doing all along, making these, like we made a Rossby number, which was the ratio of the nonlinear term, and one of the other terms, Coriolis term. We can make a ratio of these two terms. So this one's got a viscosity and a velocity and a derivative with respect, vertical derivative, so two height scales. And this one's got a Coriolis parameter, a velocity. So if I take the ratio, the velocities cancel. And I get this guy. The viscosity over F times H squared is something called the Ekman number. So how big is the Ekman number if those two terms balance? One, because they're the same size because they balance. So the Ekman number in an Ekman layer is 1. But what if I take like the whole depth and I just calculate the Ekman number for the whole depth? The viscosity will be the same. The Coriolis parameter will be the same, but the depth is going to be bigger. So the Ekman number gets small the deeper you go, which means that the friction, its effect is getting small the deeper you go, because it's saying how big is this term versus that one. If you go deep enough, the friction isn't a very important effect. It's mostly the Coriolis piece. So another way to say that the Ekman layer has a finite depth is to say, well, the Ekman number is only 1 if you get close to the surface. If I calculate it on the full depth, I get a very small number. But somewhere, if I get close enough, this thing's going to hit 1, right? Because H goes to 0, it's infinity. So at some depth between the whole depth and 0 depth, the Ekman number equals 1. And that depth, that Ekman layer, where that's true, is what we're talking about. Deviations from like a uniform flow in the vertical that happens in that layer. Okay. So this is something you can calculate quickly if you know what the viscosity, if you're given the viscosity and the Coriolis, and you can figure out how deep that is. In the real world, this one is actually highly variable. So this is somewhere between like 10 meters and maybe 100 meters. So it's not actually a very deep layer. It's like just a shallow part where there's a little bit of shear at the top. Okay, so how then do we take this equation and relate it to this force diagram? Well, that last equation was a vector equation. It was F cross V. So F cross V in the U direction is just FV. And then we get the viscosity on the U side. F cross V in the V direction is FU, which balances V. So look, there's a V talking to a U and then a U talking to a V. And there's a minus sign on one of them and not on the other, which suggests perpendicularity. So like the Y direction, that's Y and this is X. The Y direction is talking to minus the U direction, and the U direction is talking to the V direction. So if you think that out, you go, give you, it will, if they were uniform, if this was a uniform from top to bottom and this was uniform from top to bottom, it would give you this same diagram. Okay, so that's a little bit of the introduction. We're gonna come back and we're gonna look at the Ekman spiral, which is actually a solution to those equations. Yeah. As opposed to a kind of animated version.
I wondering if you could explain why the wind is opposite Coriolis, like, is that always the case, or is that this example case?
So F cross B is perpendicular to F, and F is vertical. And V is whichever direction the velocity is in. So the Coriolis is perpendicular to both of those. So it's that way. This is the velocity, Coriolis is that way. So,
Why the wind goes opposite?
why the wind goes this way is because I'm just trying to balance the Coriolis force against the wind force. Like whatever direction the wind is going, that's setting a stage. And then I say, I want a steady state balance. So I want zero net force. So my Coriolis force has to go to balance the wind force. In order to do that, I have to have the velocity going perpendicular to both. This will get a little bit clearer when we show you the solution to these equations as opposed to this kind of force diagram. But we're going to come back to the force diagram because this one is weirdly accurate in comparison to the seemingly precise thing that Ekman actually did, trying to explain all of this when he solved these set of equations. But anyway, let's take a few minutes and just talk to your neighbor about the process of reviewing and like what you found. Like, were you surprised by looking at the other papers? Like, did you learn things from the other papers? Are there still things that you're trying to do before whatever? So take a few minutes to do this. I'm gonna go refill my water. And then I'm gonna tell you some of the overall takeaways that I have from looking at all the papers and hopefully sharpen up a few of the things that were like errors that a lot of people were doing. And that'll get us in position for paper 2 to become wrong. Okay.
It's good to see like what someone who actually like has some experience in it is like guiding us. And then also the idea is just like see what
I did a little bit.
You have to like sort of like analyze what like things you have and you like by looking at I guess like I feel like it's really
And I know that.
yeah, I mean, I guess it's sort of like for a lot of buildings, it's I wasn't sure if I should like come on, try to like review them and like provide like information clarify something, or I just didn't know what those were. So like it was really difficult to figure out what I should do. Same thing happened to me. What is it? What do you think? I like first just try to write something like just write
So did anybody have any like interesting things to share that came up in your conversation about what reviewing is like? Yeah,
I think we both sort of had the issue that often like there will be like pretty like detailed technical parts within like the methodology or the like method, yeah, just the theory. And we weren't sure whether like to like request like for those things to be like more clarified more so that like someone who is more like has a more introductory understanding would be able to understand, or if that's just like normal to have that kind of technical detail.
totally. So they're part of the encapsulation of all of that into one section is so you can kind of skip over it and just jump. But in order to be able to skip over it and just jump, the rest of it needs to be really clearly labeled. So like the captions on the figures have to actually say what they're showing. A lot of times people will assume that you've read the theory section and just like refer to something that's like hidden in the middle of an equation before they give you a number. And you're like, wait, now I have to go back and read the theory section very carefully. On the flip side, the reason why we require a theory section for in here is because the theory section is the part that is closest in contact with what we're talking about in lectures, what we're doing on the homework, what the difficulties are in actually calculating the things you're calculating. That's not so obvious right now because everybody was like doing theory sections on random topics at this for paper 1. Now paper 2, everybody's going to be talking about Ekman. Everybody's going to be talking about upload. Everybody's going to be talking about temperature transport. So a lot of equations will be in every single paper because there's going to be consistency. And so then it'll make more sense. So really it's a question of audience. And if the target audience for the theory is somebody who already has your level of understanding, then it should be pretty dense because we kind of want to get it done quickly and clearly without any excess. But at the moment, that's not exactly ourselves. We're not the target audience for our own papers because you didn't necessarily have the background to read the paper you were assigned to read. So, but that's true in general. So what do you do if you really had lots of time and you had a paper that you really needed to understand, you just didn't understand the theory? That's where the use of the cited references comes in. It's like, so you should have, given in the introduction, a link, a breadcrumb trail back to other papers that somebody could go to if they didn't understand what you were talking about. They could go to that one, and if they don't understand that one, they could go to the one that one cites, and so on and so on. So like often you're crawling back this spider web of references, trying to get to one you understand, and then going back with your understanding back to the paper you're trying to get to. So that jumping back and forth process isn't so obvious at the level of detail we're operating on, but like you want to be thinking about that. Like you want to give people the references they need to understand what you're talking about. So if you just drop an idea in without a citation, you have to explain it fully. But if you drop an idea in and say, this is a standard textbook practice, see this reference, you're totally off the hook. You don't have to explain it at all. You just say, this is the answer. Go see the textbook if you don't understand why. And that's really helpful because it keeps your writing compact, but it also actually addresses all of the audiences better than you have time to do. So that's what we're going for. Other comments about that? Did you feel like you understood the paper? Sort of? You got the gist that you want? Could you see how to improve them? Like, not all, so grammatically, almost always you find typos and like things that could be improved. That's polite to point out, but that's not your job as a reviewer necessarily. You're not there to like polish the grammar part of the writing. But you should suggest if like things are unclear. So it's like, this paragraph doesn't make sense to me, is a totally reasonable comment. But like, you should have used the Oxford comma in that sentence, it's probably something you can leave aside. Right, like, unless the Oxford comma was clarified, when sometimes it is, but anyway. You know, like, you're not really, it's not grammar you're bringing, it's not spelling you're bringing. Those things are helpful because people might fix those in response to your comments, but that's minor things. The big thing is like clarity of presentation, fitting the form of what the paper is, and clarity of the science underneath. Like, did they make a leap in the conclusions they drew, or did it actually follow from what they showed?
That kind of thought, like, I feel like, I mean, I know, right? Like in, writing anything, like sometimes I'm hesitant to, like, I don't know when, like, if I can draw a certain conclusion, like, if it's like, oh, I'm actually was drawn, like, writing this, obviously you have to be like strict about, like, when you can actually say that.
Yeah.
And so it's kind of like, but it can get confusing if it's just like maybe possibly sort of kind of thing.
Absolutely.
So like that's just something I noticed, like it's like making our sort of.
So there is a rule, which after years of doing this process in classroom setting, this is the rule. If you make a factual statement, it is special. So anything that says something did something, here's cause and effect, or it is this. Those are both factual statements. In the scientific writing, you have to prove it by showing it in a piece, in like a figure. Like you can say, this is warmer than that, see figure 1. Great. This is colder than that, this is saltier than that, this is bigger than that, this is smaller than that. All those things are just right in the data you're showing. Be free to like drop all of those nice descriptions, just describe what's in the figure, and then connect it back through the introduction to the pipeline of ideas you got going. That's great. You don't always have time for that, and you may not be showing the relevant data for that to make the connection you want to make. There might be a jump of logic. Then you have to cite it. So then you say, such and such is a known consequence of ENSO. Citation. You don't get to say it's a known consequence of ENSO at the end of the sentence. That's a factual statement, it's unsupported. So that's the connection for what you're saying. Is like people might say, climate change causes this. Oh, no, that you don't get to say that unless you showed it. You have to actually find a reference that does that in order to make that connection. In the region you're in, with the variables you're talking about, like it's got to be pretty precise. Or the last one is you could say, it seems intuitive that, or one can speculate that, or a useful conjecture is that this is related to that in order to move on with the paper. But you're not allowed to do anything else other than those 3. So a lot of you will find that I just said you didn't do this. Like there's a statement there that is unsupported, and this is what it means. So just as you're like doing your edits and looking back over what you've written, just like be on the, have your radar out. Like I said something, is it true? Why? And you got to do one of these. And if it's this one, you should be clear that that's the one, like really highlight it, like say speculatively, blah, 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 whatever. Like use those code words. I noticed some people were messing around with this figure shows versus this figure suggests. This figure shows is this one. This figure suggests is this one. So you should be precise about your choice. Some of you were saying this figure suggests and then just showing it the figure, and it was like, oh no, that figure shows that. And then some more of you were saying this figure shows that here's the cause and effect. You're like, no, that figure has no cause and effect in it. It just has correlations, so that's a speculation. But you want to really get tough with yourself to do that. And if you've done that, then it's exactly that. Then when you read the paper, you don't have to believe anything they say. They're going to tell you why you should believe it. And then you get to weigh that evidence, right? So that's part of what we're trying to get to. So, and this takes a long time to get good at. All right. Other things that came up during the reviews or thinking.
I think it's something that I personally struggle with this, knowing, okay, is this a common enough piece of informational knowledge?
Yeah, it's
that
just like
I should
textbook.
cite it
Yeah,
or not? Because sometimes like then all your paper is gonna be full of citations.
yes, you can go overboard. And so there is sort of like, higher temperatures mean more heat level of things. Like you don't really need a citation for that. But like, it's helpful if it's like in the context of a discussion, then it's like falls into one of those fairly clearly. Or if you're feeling nervous, if you're like, I'm out on a limb, find a review paper or a textbook chapter that covers the whole topic and then say, for more detail, see this. And then you don't have to worry too much. That can cover a whole paragraph in terms of like factual statements you just want to build and just dump them all on one review paper. Some of you were doing that in a nice way, which is like, that's helpful. Look for review papers or those review chapters that are in that Seidler volume that I gave you, because that's exactly how you're going to get out of trouble with this. You're going to say, the North Pacific is a complicated place. Drop something, and then you're like, now I can just jump in and use all the names of all the currents because they gave me everything. It's, so that's the way you save yourself space. And it's also the way you get to the meat of what you did without messing around a lot. But you still preserve factual, whatever stuff, epistemology all the way through. Okay. Other things? All right. So when you're responding to, there's also a respond to the review. There is a peer review primer. There is a respond to peer review primer. You can look at both of them. They have these kind of clues like laid out. And most questions will address some. Okay, actual statements are special. Okay, this was one that a lot of people did. You need to find a peer reviewed reference for your data. Don't just say echo version 4, release 2, because I gave it to you. Go find Gail Forget's paper 2015, cite them. It's in the first homework that I gave you, so you can find it there. It's already in the bibliography. You can put it there, or cite Carl Winch's book, which has a description of that data set in the appendix. But give people a paper trail, because like a lot of the papers in this were like, oh, I've got data set A versus data set B, and they're different. And you're like, great. What instrument was used in data set A? What was its accuracy? You don't want to dig into all those details, but you didn't give me a place to go to look to see that was a CTD collection, and CTDs are plus or minus 0.001 Celsius. Like I needed that number because I wanted to compare your comparison, something relevant, but you didn't give me the breadcrumbs to get there. Okay? Yeah.
Would it be like citing the website when we got this?
Sometimes it can be cited in the website because some of these like Copernicus and NASA get too big for their britches. They think if they put it on their website, it's the equivalent of publishing. It's better that they normally have the like descriptive paper at the bottom underneath the description of what it is. It's better to point to that. And then you can say downloaded from. So give that one and then say downloaded from a website and give a URL. But there are questions to be answered that are not on the website that a reader might need to know, like what's the accuracy of the instrument, which doesn't normally get mentioned on the website. Does that make sense? I mean, later in life, when you know these things and everybody in your business is all using the had SST data, you don't have to do that. But for now, like, let's do it because it's good practice. And you probably shouldn't even be doing it later. Okay? And right now, also, it's difficult for you to tell which data sets are really common, well understood ones, and which ones are like totally obscure that you found on some weird web page. like, they all seem the same, they're just magical things on the internet. So you find that, find some paper trick. Okay, so a couple of things got left out in a couple of papers, so I pointed this out before, so the required things are in red. Suggested things were in this sort of whatever light green, but some people forgot to put their name and the date on the first page. Please put your name and the date, because when we put it on the web page, that's nice. Okay, one. Some people were introducing data but weren't quite sure where to put it. Like normally it's in the methods or theory and methods. There will be a, data used in this paper section. It shouldn't go in the results and it shouldn't go in the introduction. It can go in there. And then all of your figures and tables need to have captions. And they need to be kind of detailed. Like they should say, if you read the paper, I make this point in the paper primer, but anyway, I'll say this again because this is really important. The fast way to read a scientific paper is you read the abstract and the figure captions and nothing else. You should be able to read your paper like that and understand what it is. So the figure captions need to be adequately precise about what's in that figure, that if you skip all the other sections, you still know kind of what the paper is about. And then you could drop in on the conclusion and see if you agree with their interpretation of figures with your interpretation of their figures. All of the extra text is to help if you're like, I looked at a figure and I didn't understand that figure. Now I can go to the text and like dig in and like see what the discussion about what that figure is trying to show. That's helpful. Or I don't know what that word in the caption means. So you go to the theory and method section, you find the equation that describes what that word means. And you're like, okay, now I can go back to the figure and interpret it. But you shouldn't have to read the paper linearly to understand it. You should be able to skim very quickly, just abstract captions and get the gist. The next level deep might be introduction and conclusion. Then if you're really studying the paper, you're going to go back and read the theory and results and discussion in great detail, linearly front of the back. So keep that in mind. That's also the way you should review the papers, is like focus on those pieces, those highlighted pieces, because those are the most important parts. Those are the things that are structuring the order of ideas, and everything else is kind of filling in around. Does that make sense? Okay. This is another thing. So, this Pablo Picasso quotation. You're looking at these other papers and things. You're peer reviewing these other papers. You're peer reviewing. You're citing other papers. Look at their format, the way they're using language, the style of their captions, the units and how they're described, and the standards, and just copy. Just do exactly what you're learning from reading the other papers. We're not trying to be inventive about structure here. We're trying to master a form. And the form is pretty complicated and pretty messy. So if you look at your paper and like, doesn't read like the papers I'm reading to cite in the introduction, try and figure out what is different. Like, what are the pieces you can mimic? Because that's where we're trying to go. Like, in a stylistic sense, we want all these papers to be totally homogeneous. It's kind of boring, but that makes the science stand out, because then the science is the only distinguishing characteristic. And that's the goal of these papers. They're supposed to be able to be read really fast, highlighting the key innovations in your scientific approach, and none of the other presentation and stuff is getting in the way of that quick appreciation. So that's why everything is so structured. It's why everything is so formulaic, is because it's like a newspaper article. You're trying to, you just read the headline and then the lead, and you're like, do I need to read the rest of this? Maybe not. Like, that's what a science paper is. That's the title and abstract. Do I need to read the rest of this? No, I'm not interested in that. Or yes, but I only need to read the part that they mentioned here that I find in figure 4. Like, or I just need the bibliography. You don't care about the rest of the paper. Like, it's meant to be really structured so that you can read it non-linearly and go through many papers fast, which is why you also get to cite a lot of papers, is that you're learning how to do that, right? Does that make sense to everyone? Okay, But this is good. Everybody's making progress. Like, this is the game. Okay. Are there any other questions about papers, or we can go back to Ekman? His name is Ving Volfried or something. I don't know. Anyway, very like Scandinavian guy. Okay. All right. So Ekman. So Ekman came up with these same equations we were just looking at. These guys here. It's maybe a little better rather than writing VE, that little extra bit of shear, to say it's the velocity as it deviates from, let's say, the vertical average. So if everybody's Taylor-Proudman except for at the top, the deviation from the vertical average is what we're talking about. And same in the U direction. And just like we pointed out, the V velocity talks to the U friction, and the U velocity talks to the V friction, because these two equations are coupled, because the Coriolis is a weird force that goes in a different direction than the rest of the terms in the equation. Okay, so, all right. How does the wind stress come into this game? Well, the wind stress is actually a boundary condition on the shear at the surface. So the viscosity times the shear at the surface times the density is the wind stress in that direction. So if you think of a shear profile, like, here's our little profile. The slope here, as we hit the sea surface, is proportional to the wind stress. That's what that means. That's true in both directions, because we could have a component of wind going this way. So we have another one of those over here for the Y direction wind stress. Okay, so now look at this. Straight up from a differential equations perspective, what do we got? Two coupled second order ordinary differential equations with two boundary conditions at the top. And then as we go to infinity, the U is just going to equal that U bar. As we go below the Ekman layer, the Ekman effect decays. So we're going to 0 at the bottom. So we have a nice structured ordinary differential equation setting with stuff, second derivatives, first derivative specified on one boundary, values specified on the other boundary. Okay. So it's not as easy. Often you would say, oh, just sines and cosines, and I'll figure out the details later when you have this, or exponentials or something. It's a little more complicated because the V talks to the U and the U talks to the V. So you have to like mess around and like get all the angles in, but that's what Ekman did. So Ekman solved that set of equations, wrote that set of equations, made this set of assumptions, and then solved them. And here's the solution, which is pretty complicated. So there's a factor, e to the z over d. So there's an exponential decay as z goes to the bottom. And that's true of both components. But we knew that. It's got to go to 0 as you go to infinite depth. Fine. It exponentially decays. Times these funny cosine and sine factors, which is like really hard to figure out, but they're also going in z over d. So it's like this term is oscillating. This term is oscillating in a different phase. This term is oscillating at the same phase as that. This term is oscillating. So what does that all mean? It means this. It spirals around in a clockwise direction as you go from the surface. Okay, so the velocity is largest at the surface, and it's not in the wind direction. It's 45 degrees off of the wind. And then the next one down is a little bit more than 45 degrees off. And the next one down is a little bit more, and they're getting weaker. And so if you drop these all down onto a surface, this thing's called a hodograph, which is where that spiral is projected onto one plane to show you all the depths at once. Okay. So this is called the Ekman spiral. And it's a particular simplification. It's a solution to this simplified equation set with constant viscosity in the vertical, with simple boundary conditions that are fixed in time, and with this with a steady wind stress. So without any just a fixed and fun. Okay. This prefactor has an F in it without any squares or anything. So F in the northern hemisphere is what? Positive, it's up. And in the southern hemisphere, the rotation axis is pointing into the ground, so F is negative. So that means the whole solution, the spiral part, goes the other way in the other hemisphere. It's the lunar reflection. So instead of going clockwise as you go down, it goes counterclockwise as you go down, which you can simply do by flipping the figure in the horizontal, which is why all the words are back. Yeah.
Maybe this is like the wrong time.
Yeah.
Maybe earlier might have been better, but in like the 8.3 UC equation.
Yeah.
You're multiplying like the standard density of water.
Yeah.
Times like is that the dynamic viscosity?
So that's this eddy viscosity, but it's a dynamic viscosity.
So would the density like go away in the like term? Or would you just use the dynamic viscosity instead of just the kinematic viscosity or something?
Oh, yeah. So this is really just because the units of tau are funny.
Okay,
So tau is a momentum.
Yeah.
And so what you really, the easy way to think about it is that way. This is the thing that we're messing with. This has units of like meters squared per second. This has units of meters per second. This has per meters. Put all that together, you get something that's just meters and seconds. So you got to kill out kilograms that are in the stress part of this.
okay.
And the reason why we talk about tau at all, which will come up in a second, is that if there's a tau here pushing on the ocean, there's the opposite tau pushing in the atmosphere, but they have different rows. And so the tau is the thing that's actually the boundary condition. The shear will be different based on the density of the atmosphere versus the density of the ocean. Does that make sense?
Yeah, I was thinking, why does it not cancel out with the viscosity density? But
Yeah, I mean, we can hide it in a different way.
But it-
But this is sort of, it turns out this is convenient, but it doesn't look convenient at this moment. So there's no row down here, for example. Oh, there's a row here. But it's over tau. It's exactly that. The row is tau over row. But that's the only way that it comes up. Yeah.
Is D like bottom that?
D is this Ekman depth, like as deep as that layer goes. So it's
Z is going from
it's-
0 to X.
0 to minus. Z is minus D. Yes.
Okay.
0 at the top and then it goes
Oh,
down.
Z is negative.
Yeah, Z is a negative number in this. So Z gets more and more negative and it
Okay,
goes to 0. E to the minus
and
Z over D.
so it's decay because
The more negative Z gets, this decays more and more. Every time it drops by a factor of E, every D distance from the surface.
oh, Z can be greater than D.
This is Z. This is 0.
And
Here's
if you're okay,
minus D. And then minus 2D, it's almost D.
yeah, okay.
Yeah.
And then does the spiral come back on itself?
It comes around and yes, it'll go all the way around, but it's like,
Really
it's
small.
vanishingly small.
Okay,
If you didn't have this decay factor, these would just go around and around. Right, because cosine and sine would just spin around in circles. This is capturing the amplitude decay. Okay. So this is all very pretty. This is all nice. This doesn't happen in the real world. Hardly ever. It's a really nice way to think about this problem, but it's too idealized. This happens in the real world. So how does this relate to this? Well, the details we talked about a force diagram that was like the total wind and then the total Coriolis force are in balance. But the total Coriolis force is a little bit of the Coriolis force from this one, and a little bit of the Coriolis from this one, a little bit of the Coriolis from this one, a little bit of from this one, and so on. So those are all spiraling around too. It's only their sum over the Ekman layer that has to balance the wind and the. So it's the vertical integral of the Ekman spiral that balances, that has a Coriolis force that balances them. And you might say, well, how does that work? Because isn't there a force balance on like this random guy part of the way down? Shouldn't it also have a wind stress and then a Coriolis force that balances it? No, because it's also dragging on the one above it and the one below it. So it doesn't have a wind stress. It's got a friction against the one above and a friction against the one above and then a Coriolis. So those three have to be in balance. Then you go to the next one down and this got a friction on the one we just talking about, friction on the next one, and then a Coriolis in a different direction. So you have a new force balance and a new direction for every one of those arrows all the way down, which you can actually do out if you really want to from this formula. You can explore that and see that it actually works. But this is extremely detailed. And it really, really matters that this guy is constant. Because we use a constant coefficient solution to an ODE to get this. In the real world, this thing is made by turbulence, and the turbulence varies a lot in the vertical. So it might be really intense turbulence, big eddies going fast at the top, and a little bit lower. They're littler eddies going slower, and then a little bit lower. That means that the eddy viscosity changes in the vertical, which means that this solution does not apply. But magically, the integral, this part still applies. Because it doesn't matter how you distribute that shear, when you integrate over the whole layer, Coriolis force integral over the whole layer has to equal the wind. That's the balance you want, which means that the integrated velocity over the whole spiral, the net transport of that layer is going to the right of the wind or the left of the wind of the sun. Okay. So that's why I did not derive the Ekman solution. It's just a fun ODE activity. I just gave you the answer. You can plug it into those equations and convince yourself that it works if you want. But really, it's actually not that useful. So people have gone out in the ocean and really tried to observe the Ekman spiral, and you kind of can. But it's not actually a very stable object because under normal conditions with a big wind, it's varying time. It's like a turbulent, crazy boundary layer. The only thing you know is that the average wind is going to, on average, drive a current perpendicular to it, integrated over the whole layer of wind input. Okay, that's the robust result, and that's what we're going to use as we go on. Questions on this? Okay. All right, so this is me saying the typed words, what I just said. This thing is the transport, it's the vertical, or there should be DZ, vertical integral of the velocity, which is balanced by the wind stress over F times tau, with that cross Z to give you that 90-degree part. Okay. So this whole thing happened because this is like the oddest couple of all time. So Ekman is Nansen's student. So Nansen was out in the Arctic, like frozen, like trying to cross-country ski to the North Pole, like we talked about, the whole totally crazy guy. He comes back and he's like, the icebergs don't blow downwind, they go sideways. They go to the right of the wind. And then Ekman was a student and was like, let me formulate a mathematical theory to see that that will be right. And that's how he came up with the whole Ekman spiral notion. And it sort of gets that part right. It gets the idea that the surface current is going to the right of the wind. And how deep the iceberg goes and all those complications are part of that story. But you would get the sense that the icebergs would not move downwind, they'd move to the right of it. So that's the storyline. where this all is. So we have two visions in mind. This calling chapter 3 is really a nice place to look at these sort of dynamical ideas. I gave you a link which may or may not work. So I gave you another link in these slides that goes to just a Dropbox version of that chapter. So you can go look at my version. You can't get the Brown library version to work, which I couldn't. But we should have two visions in mind. So here's the depth of frictional influence, or the depth of wind influence. The Ekman spiral extends over that. And the vertical average of the Ekman spiral would be perpendicular to the wind, which would have a Coriolis force balancing the wind. Okay. That's our concept. Okay. So the last thing we want to talk about is, why do we care? Well, we care because there's all kinds of interesting things that happen if you take winds and put them next to things and make them blow currents perpendicular to the wind. For example, at the equator, in the northern hemisphere side, the Ekman current is going to flow to the right of the wind. On the southern hemisphere side, the Ekman current is going to flow to the left of the wind, or the Ekman transport. So that means that if you have trade winds that go from east to west, which we do, the equator is going to have diverging surface flow, which means the deep water is going to be drawn up and reappear at the surface, bringing cold water, nutrient-rich water up all along the equator in all of the basins. We're going to keep, so equatorial upwelling is one signature. What about if we're right next to a coastline and we blow a wind along the coast? Blow a wind along the coast in the northern hemisphere, it would push the Ekman transport offshore. Where does that water come from? Well, it's got to come from below because there's a coastline over there. So all along the coastline, if you in the northern hemisphere, if you have an equatorward wind along the coastline on a west coast, you will have an upwelling region. And it turns out that almost all west coasts in the world have a wind in this direction, at least for some seasons. And so they have an upwelling zone. This is why San Diego is colder in the summer than Providence. Because there is cold ocean water being pulled up from deep. It makes a whole marine layer cold thing happening at the surface because the wind is blowing from the north to the south along the coastline of California, pretty much all summer months. Okay. And all we used to get there was the Ekman transported to the right of the wind. That's the takeaway. So the right of the wind in the northern hemisphere, the left of the wind. If you look from the side, it's this kind of thing. You're expecting to draw the deep water up to replace divergences. That's true in this case and in this. What if the wind changes instead of the coastline changing or the Coriolis parameters? You also get interesting effects from the Ekman transport. So if there's wind going this way and wind going that way, just to mean that there's a curl in the wind stress like this, a negative curl in the wind stress. This one will push the Ekman transport that way. This one will push the Ekman transport that way. So they converge and go down. If you put them the other way, so there's a positive curl in the wind stress, they diverge and pull stuff up. So at the bottom of the Ekman layer, you expect there to be a vertical velocity that's proportional to the sign of the wind stress curl. So we will find that the wind stress curl is the thing that drives all of the gyres because of this vertical velocity induced by this kind of spatial variation in the winds. So this is a bit obscure now, but we're going to spend like literally the next class just talking about this effect. It will become very clear what I mean by this, but it takes some practice. But here's sort of the equations supporting that same idea, which are useful when you write the paper about it. Okay. So, does this matter? Well, here's observations of chlorophyll. Here's observations of temperature. If you look, where are big chlorophyll anomalies? There are chlorophyll anomalies along the equator in all the ocean. That's because there are trade winds blowing this way. It's pushing the Ekman transport out, pulling up deep nutrient-rich water into the light, and it does it consistently all the way around. Oops. See if I can move this. Where else is there a lot of chlorophyll? Look at along all these west coasts. There's an awful lot of chlorophyll on all of the west coasts. That's because there is an equatorward wind along the west coast, and the equatorward wind is pushing offshore Ekman transport, which is upwelling, bringing deep, cold, nutrient-rich water to the surface. If you look over here in SST, you see, look, there's cold all along the Peruvian coast, cold along the US West Coast. There's a seasonality to it. So these winds aren't always going in that direction, but it's coming and going. West Africa coast, a little bit here, kind of in the Canaries. And then the western side of Australia also has it. That's all Ekman upwell. It is making the cold water be there. It is making the chlorophyll be there. There's a kind of general subpolar and subpolar effect. That's because the winds in that region are going in this direction, which means that you have upwelling throughout, which means that there is replenishment of the surface nutrients in all of the subpolar regions. So the Ekman curl of the wind strap, the Ekman part is pulling up nutrients into the light all over those subpolar regions. So in one day's worth of theory, we've explained the major deviations in chlorophyll almost everywhere in the world, and the major deviations from zonal mean temperatures almost everywhere in the world. So it's a lot to do. We're going to come back to this again and make sure that this is all grounded. For the next paper, you can pick one of these regions and start looking at it. What's the wind stress doing? What's the Ekman transport doing in response? What does that do to the densities? Can you diagnose the whole thing in echo? Can you see that shear in the near surface? Pull it out, balance that shear versus the wind stress as it changes season by season. How much stuff does it transport? All of those questions are things that we're going to do for the next time around. Cool.